Chapter 10, Deduction and Induction, a closer look. Now, when you're attempting to identify an argument as to whether it's deductive or inductive, just ask yourself, is the author attempting to prove the conclusion is necessarily true, or are they simply giving you good reason to think that it's likely true? If it's a deductive argument, then you're going to infer that the author suggests certainty, and they're typically going to use terms such as must, all, and necessary. If the author is simply attempting to convince you of the likelihood of the conclusion, they're going to use language such as probably, it is likely, it's reasonable to conclude, etc. So that's how you can tell the difference between the two. It's all in the intent of the author, and you can infer that by taking a look at some of the language used. Now remember that these terms, valid, invalid, sound, also strong, weak, and cogent, which we'll talk about when we get to inductive arguments in a minute, these are technical terms used in a special sense. So make sure you understand these technical definitions because these words are thrown around in everyday conversation to describe arguments that we may or may not have good reason to believe, but in a philosophical sense, in academic philosophy, they mean something very special within the context of logic. And of course, a valid argument is a deductive argument that if the premises were true, the conclusion would have to be true. If it's an argument that's deductive in which that even if the premises were true, the conclusion wouldn't necessarily have to be true, then it's invalid. And if it's a valid argument with true premises, now it's called sound. And notice that validity and invalidity, those concern the argument's form, its internal logical structure, whereas soundness has to do with form and the content because you're saying something about the truth value of the premises. Now, one way to test arguments to see whether they're valid or invalid is to simply ask yourself, are there any counterexamples? And there's some excellent exercises in the book in 10.1. And Herrick invites us to think through these informal arguments and to ask ourselves, is there any way in which the premises could be true and the conclusion false? And if that is the case, then it's invalid. If there's not a way, then it must be valid. So here's the way that number one is written. Since some Hondas are purple and some Hondas are trucks, it necessarily follows that Honda makes at least some purple trucks. What do you think? If those premises were true, would they force the conclusion to be true? Or can you consider a counterexample? One way to think of a counterexample is just to simply visualize the premises. And so here, and first I've formalized the argument. So premise one, some Hondas are purple. Premise two, some Hondas are trucks. Therefore, conclusion three, some Honda trucks must be purple. But you can see the premises visualized here on the screen. So on the left, that circle concerns, that's a category that includes all purple Hondas. And you can see that X in there means that there are some. That's the first premise. Some Hondas are purple. Okay, fine. Second premise, some Hondas are trucks. All right. Right side, you got a circle. That's the category of Honda trucks. There's an X in there. That means there are some of them. But the conclusion attempts to say, therefore, some Honda trucks must be purple. From the premises, that's not the case. They don't have to be purple. Now, the premises have also not told us that these categories are mutually exclusive. I've simply drawn them that way. And so I could have had those circles overlap, and there probably are some purple Hondas out there. But just based on the way the premises are stated, there's no reason to necessarily draw that overlap or conclude that some Honda trucks are purple. And so therefore, this argument is invalid. We can see that, and we can also articulate a counterexample. Here's another one. This one's interesting. I want you to think about it. This is number four. The U.S. House of Representatives has more members than there are calendar days in a leap year, meaning there's 366 days in a leap year rather than 365. Therefore, at least two members of the House must have the same birthday. So the U.S. House of Representatives has more members. They have 435 members, by the way. More members than there are calendar days in a leap year, which are 366. Therefore, at least two members of the House, at least two of these people, have to share the same birthday. What do you think? Is that a valid argument, or can you consider a counterexample? Well, let's look at the math. So a leap year has 366 days, and there are 435 House seats, and therefore 435 House members at any given time. So up to 366 people could have different birthdays. So if there are only 366 members of the House, then these folks could all have different birthdays. In fact, if you were considering the members of the U.S. Senate, the U.S. Senate has 100 members, two from each of the 50 states. And so all of the members of the Senate could, in fact, have different birthdays. We're talking about the House of Representatives, which has 435 members. And so if you look at that 435 members and you do a little bit of math, you're going to realize that there are 69 more members of the House than there are days in a leap year. Therefore, there are going to be 138 members that share a birthday with another person. It has to be 138 because you've got that 69 that's over the 366 threshold, right? So all those people aren't going to have a unique birthday, and they're going to share a birthday with 69 of those 366. So you've got every day accounted for in the first 366, January 1st, January 2nd, even February 29th, because it's a leap year. Each of those days accounted for up to number 366. But now you have number 367 to number 300 or 435. That's 69 more people, all of whom are not going to have a different birthday than any of these 366. And for each one of those persons, they're also going to match the birthday of one of those people that was of the first 366. So you have to multiply that 69 by 2. Now, it could be the case that up to 297 have unique birthdays. That would be 435 minus 138. But in any case, this argument more than works. It's very much valid because the way math works out, if you go back to the original argument, the U.S. House of Representatives has more members than there are calendar days in a leap year. Therefore, at least two must have the same birthday. It's more than two for sure. So that argument's actually valid. And here's one more. You'll get this one. Simple. Listening to loud music always ruins your hearing. Joe is hard of hearing. Therefore, Joe must have been listening to loud music. Can you think of a counterexample in which the premises are true but the conclusion false? So listening to loud music always ruins your hearing. I'm not sure it always does that, but we're going to assume for the sake of argument, for analyzing the internal structure and determining whether it's valid or invalid, if that is true. Joe is hard of hearing. Imagine that both of those are true. Therefore, Joe must have been listening to loud music. Can you think of a counterexample? Yeah, of course. Maybe Joe has a congenital hearing issue. He was born with not the best hearing. Maybe Joe worked at a job, a construction site, which was very loud. He wasn't required to wear adequate hearing protection. Maybe Joe was in the army, in the infantry, and he fired very loud weapons, and that's the reason that his hearing is damaged. So it's not the case that this particular argument is valid because we can think of several different counter examples. Okay, categorical deductive arguments. These are a type of deductive argument. We're going to consider several different types in which you're going to hear about different categories, hence the name. And so you'll see keywords such as all or no or some. And so these are some examples from earlier in the semester. All whales are mammals, no mammals are fish, therefore no whale is a fish. I don't think I called them categorical deductive arguments at the time, but we're going to call them that now because that's what they are. And if you see those highlighted keywords such as all, no, some, etc., then you're talking about categorical deductive arguments. And you can visualize these like we did earlier with the different categories in different circles. And so here's a basic categorical deductive argument. All zombies are mindless slaves. All mindless slaves lack free will. Therefore, all zombies lack free will. And you've got that category of all zombies being mindless slaves down there toward the bottom, that smallest circle, and that's represented by the first half of premise one. And then you have the category of mindless slaves. You can see the zombies are fully within that. There are no exclusions outside of that. And then in premise two, you have all mindless slaves lack free will. So you have things lacking free will. All the mindless slaves are within that. All the zombies are within that. Therefore, the conclusion does in fact follow. All zombies lack free will. Of course, this is for the sake of argument and analyzing the internal structure and to see whether it's valid or invalid. Maybe you've read a book where zombies gain free will. I don't know, but it's the way we're defining it here. Sentential deductive arguments. These are deductive arguments in which you're going to see these various operators. So you've got modus ponens and you've got modus tollens. And these are a couple of arguments that we considered last chapter. And these are valid argument forms. So if P then Q, P therefore Q. And if P then Q, not Q, therefore not P. Remember, that's modus ponens and modus tollens. But last chapter, when we considered the various fallacies, we talked about the fact that denying the antecedent is fallacious, and so too is affirming the consequent. So if we were to say, if P then Q, not P, therefore not Q, well, that's not necessarily the case. And we know that's not necessarily the case because just a second ago, we considered this particular argument about there being a counterexample. And you could say all people who listen to loud music, actually, that's not a good example at all. So if we had the example, say for example, trying to think of a good fallacious example and better at the actual valid forms, but if we said if P then Q, not P therefore not Q. So and I used this example before, I think. So if I execute a perfect armbar, then my opponent will tap. You could say, I'm not executing a perfect armbar, therefore my opponent will not tap. Well, of course, they may tap for some other reason. So that helps illustrate why denying the antecedent is fallacious. And the second one is affirming the consequent. This is when you don't deny the consequent, which is modus tollens, which works. But if you were to affirm the consequent and say, if P then Q, P therefore Q, if I execute a perfect armbar, my opponent will tap. And then you're saying my opponent's tapping, which would be Q, you're affirming that. That would not mean that you're necessarily executing a perfect armbar. You could simply be executing a triangle choke instead. I like the MMA example is better than trying to think of one on the fly or connected to that other one, I suppose. All right, here are some different types of sentential deductive arguments, and they're going to use this top one, for at least, is going to use the operator or. So this is actually what's called a disjunctive syllogism. It's a common form. And the second one is a hypothetical syllogism, which is kind of an if-then chain. So the disjunctive syllogism is just an either or, and the hypothetical syllogism is a if-then chain. So for the disjunctive syllogism, you're going to say either P or Q. Not P, therefore must be Q. So you could say tonight, we're either going to stay home or we're going to go out. We're not staying home, so we are going out. So that's a valid argument form. If it were the case that you only had those two options and you're going to do one or the other, and you're not doing one, then you're necessarily doing the other. And of course, it could be not P, not Q rather than not P. It doesn't matter which of those that you put the little tilde for not in front of. Now, for the hypothetical syllogism, you've got if P, then Q. And then you have if Q, then R. And now you're going to make a connection between the first and the last, between that first antecedent and between that and the second consequent. And that leads to the conclusion of therefore, if P, then R. It's just a chain. If you're connecting things in a chain that shouldn't be connected, that don't really follow, that's fallacious reasoning. Don't do that. But if it were the case that if P, then Q, and if it were also the case that if Q, then R, then it would have to be the case that if P, then R. Now, this sentential logic is also called propositional logic. And just for your awareness, is the foundation of computer coding and algorithm design. So, but for this cool logic stuff that humans have been working on for a few thousand years, computers wouldn't have their cool coding language, wouldn't have algorithms, including AI. So thank you, philosophers and logicians. All right, now that we've talked about modus ponens, modus tollens, and disjunctive syllogisms, and also hypothetical syllogisms, let's take a look at exercise 10.5. Let's look at number 2. So this exercise is going to ask us to identify this argument form. Which of these is it of these four, or does it not apply at all? Amber jogs today, or Barbara jogs today. Hopefully you know what this is already. It's not the case that Amber jogs today, so not Amber. Therefore, Barbara jogs today. Now, of course, that's going to be what? The disjunctive syllogism. That's that either or. Yep, that's a simple one. Here's another one. Number 3, if Amber jogs today, then Barbara jogs today. Amber jogs today, therefore Barbara jogs today. So you've got affirming the antecedent, which is legitimate, it is valid. It's called what? Modus ponens. Very good. And here's the last one we're going to do in this particular set. Number 4, if Amber jogs today, then Barbara jogs today. It's not the case that Amber jogs today. Therefore, it's not the case that Barbara jogs today. Which of those reasoning forms does that match up with? Is it modus ponens, modus tollens, disjunctive syllogism, or the hypothetical syllogism? Well, it's not that if-then chain, so it's not hypothetical syllogism. You don't see the word or in there, so it's not a disjunctive syllogism. You do see a not the case, but the way modus tollens works is it denies the consequent, the second half of that if-then conditional statement. But the way this is set up, it's denying the antecedent. So it says, if Amber jogs today, then Barbara jogs today. It's not the case that Amber jogs today. Therefore, it's not the case Barbara jogs today. Well, the way this is written, the way the conditional in premise 1 is written, Barbara could jog on her own, independent of whether Amber jogs today. It doesn't say Barbara jogs today only if Amber jogs today. It doesn't say that. It just says if Amber jogs and Barbara jogs. But then premise 2 says Amber is not going to jog today, but that does not rule out the possibility that Barbara could jog today. So this one is not valid, and therefore it would be not applicable to NA, none of the above. Remember, invalid in this technical way that philosophers and logicians use the term does not mean false, for validity concerns the argument's internal logical form, not the truth of its premises or the conclusion. Soundness, however, does involve truth values, for sound equals a valid argument with true premises. And as Herrick puts this clarification, an argument could have faulty reasoning, but true premises. You could have screwed up logic, but premises are true. And you could have an argument with fantastic reasoning. The internal logic looks great, but the premises themselves are false. And so too is the conclusion. So don't mix those two things up. Now, Herrick also includes in this chapter two ways to effectively object to an argument. And one would be to show that its internal logic is screwed up. Another way would be to call into question the veracity, or not the validity, but the veracity means the truth of the premise, or at least one of the premises. Call into question its truth. A way to ineffectively object to an argument would be to instead argue for a competing conclusion. And Herrick argues that this is a poor way to evaluate or to object to an argument because it does not directly engage the argument. So if someone offers an argument, you don't think it's a good argument, you don't want to buy the conclusion, you prefer some other conclusion, please look at the argument itself and ask yourself, is there something wrong with the premises? Is there something wrong with the internal logic? If not, maybe you should abandon your argument, adopt theirs. Don't just simply continue to argue for yours. Think about theirs. Ask them questions about theirs. Help them think it through. Maybe it really does have some issues, and maybe if you help them think about it, you both will come to a better understanding. All right, here's a knowledge check. This is exercise 10.7, and the question here is, are these statements true or false? Statement number one, some deductive arguments have true premises and yet are still invalid. Some deductive arguments have true premises and yet they are invalid. That's true. Yeah, remember the validity, that's testing the internal logic, and that's separate from the truth value of the claims themselves. So a deductive argument could have true premises, could be completely true and still be invalid, still not be the case that the premises force the conclusion to be true. Number two, some deductive arguments are invalid and yet they have a true conclusion. You think about this one. Some deductive arguments are invalid and yet they still have a true conclusion. Yeah, that's also true because it doesn't matter. There's no connection between validity and truth. Validity concerns the internal logic. Truth is something else that concerns whether or not the claim corresponds to reality. And so you could have an argument that has terrible internal logic, but the conclusion is true. So for example, Matt is recording a lecture video right now, is the conclusion. And because the sky is green and because it's April Fool's Day. Well, it's not April Fool's Day. The sky is not green, but I am recording a lecture video right now. So there's an invalid argument with a fully true conclusion. So those things are separate. Number three, a deductive argument can have false premises and a false conclusion and yet be valid. A deductive argument, remember deductive argument just means it's intended to prove the conclusion is true. It can have false premises and a false conclusion, yet be valid. What do you think? Yeah, you could have a completely valid argument that has something to do that is a completely imaginary. You could make a valid deductive argument about fictitious characters in a world that doesn't exist using laws of physics that are false, and it could still be a valid argument. Number four, some sound arguments have false premises. Well, to answer this, whether it's true or false, you need to ask yourself, what does it mean for an argument to be sound? And a sound argument is one in which it's valid with true premises. And so this says some sound arguments have false premises. No, they do not. If it's a sound argument, it necessarily has true premises. Otherwise, we wouldn't say that it's sound. And number five, some sound arguments are valid. Some sound arguments are valid. Let me think, what's the sound argument? Oh yeah, it's a valid argument with true premises. And so yeah, all sound arguments are actually valid. All right, that's deductive arguments. Let's move over to inductive arguments. And here are some definitions that are structurally similar to the definitions we just considered from deductive arguments. With deductive arguments, you have valid, invalid, and sound. With inductive arguments, you have strong, weak, and cogent. Cogent is very similar to sound, except we're talking about inductive arguments. So a strong inductive argument is one in which we do, in fact, have adequate reason to believe the conclusion is likely true. A weak inductive argument is one in which it does not provide enough reason to prove the conclusion is likely true. And a cogent inductive argument, that's one that is strong, so we have good reason to believe the conclusion is likely true, and the premises are actually true. So that's what we want. And that's what you're going to look for and find in the real world are these cogent arguments. The valid arguments, this stuff is interesting. You do need to go through these exercises to strengthen your logical reasoning skill. You need to be sharp in that way. It will help. It'll help in math class and help in reasoning in general. But in the real world, you're not going to find too many valid arguments in this technical sense, but you will find a lot of strong, weak, and you're looking for those cogent arguments. So this is the stuff that's more practical for real life. Three types of inductive argument that we're going to consider. There's other types, but three we're going to consider. One is argument by analogy, very common. I use it quite a bit in my focus area, which is applied ethics and political philosophy. Enumerative induction, something that's also very common in the real world, and I suspect that you use it. I'm sure you've used it many times. And then last, inference, the best explanation. You use that as well, even if you're not a detective such as the great Barney Fife. So first of all, argument by analogy. This draws inferences between relevantly similar things. And that's the key. The two things need to be relevantly similar. And you'll find an argument by analogy in lots of different areas, including the medical field. Pharmaceutical companies will test a new drug compound on monkeys, and they'll say, hey, it made this monkey grow hair, or it cured this monkey's diabetes. Now, there's good reason to think that it may or probably will be effective on humans as well. Maybe you wouldn't say probably will be so quickly because the stakes could be so high with side effects and such. But if you do enough tests on enough monkeys, that's going to give you a reason to apply for clinical trials because monkeys have relevantly similar biologies to our own. And so if it works on mice, okay, fine, at least they're kind of similar to us. But monkeys are very similar. Now that would give us reason to at least apply for those clinical trials that begin those with, of course, rigorous ethical standards. Argument by analogy, very, very common in the legal world. It's the foundation of the legal system, treating like cases alike. And judges will say what they have to do is they have to follow legal precedent. They're going to look at the case law. They're going to look at statutes, actual laws, and they're going to try to interpret and apply those in ways that are faithful to the legislature's intent. But they're also going to take a look at the way judges have ruled on similar cases. And so they're going to say the facts in this particular case are relevantly similar to the facts in this other case. And this other judge ruled in this way, and I agree that the reasoning made sense. So therefore, we should, as a matter of legal precedent, because that's the way the legal system works, rule similarly here. That's treating like cases alike. And that's also a principle that we take for granted as being a moral principle that people should and have followed as a matter of intuitive morality and ethics throughout time, that we should treat like cases alike. And what we do here is we say this situation is relevantly similar to that situation, so we should treat them similarly. And in some cases, the best moral arguments by analogy shed light on some situation where there's a question about what should be done. There's a famous one by an Australian moral philosopher named Peter Singer. Peter Singer said, in a nutshell, if you were to be walking past a shallow pool, see a small child drowning in that shallow pool, and if you were to think to myself, should I jump in and save that kid or not? And you might think immediately, yes, I certainly should, but you might pause for a second and say, oh, I'm wearing my brand new shoes. If I jump into that shallow pool, that shallow pond, it's going to ruin my brand new shoes. But you probably would conclude that that kid's life is a lot more important than your shoes. And therefore, you would jump in and save them anyway. If you agree that that's quality moral reasoning, if you agree that in that case, the kid's life is more important than your new shoes, well, Singer argues that the next time you're out shopping for new shoes, you should go back home, wear the shoes that you have, and donate that money to a charity such as Oxfam. They can then use it to purchase very simple medications to save the lives of actual children in the third world. That's his argument by analogy. And the way you analyze an argument by analogy is you ask yourself, are there any relevant dissimilarities between these two things being compared? One dissimilarity would be that you've got a kid drowning right in front of you versus a kid drowning or dying of diarrhea, for example, in a country that's thousands of miles away. Is it a relevant dissimilarity that the kid's either drowning right in front of you or dying of diarrhea far, far away? Singer would say no, the kid's life is just as important in both cases. You may not be as morally touched, you may be able to shield yourself from that connection, but it's still a human being, it's still a child, and you can still save them. You can think more about that argument if you want to, or take my ethics class and we'll think about it together. Enumerative induction. This is another common argument that is of the inductive form, and this is going to be simply a generalization from a sample. And you want to ideally have an adequate sample size. Take a stats class to figure out what that size should be and how to do this in a quality fashion. You want to have variation of that sample, make sure it's pulling from lots of different examples within that pool or that thing that you're attempting to judge. And if you are random in your selection, you should get that variation. So you're going to get lots of different random samples. And you could use this, for example, to predict a sports opponent's next play. You can look at their film, look at what they're doing that particular day. What have they done in similar situations? That would give us strong reason to believe they're going to do something similar, although a good coach may realize that you've studied the film and then do something completely different, throw you off. Or you could predict an election by polling likely voters and doing it in a way in which you actually get to the likely voters. There have been some pollsters in recent presidential elections who have really botched their predictions because they attempted to call people with landlines. Well, in this day and age, few people still have landlines, and so they were just reaching out to people of a particular uh, age and possibly voting persuasion, and so that skewed their numbers. And so you want to make sure it's actually random, that you actually get that variation needed, and it's actually a sampling of what you intend to draw an inference about. In that case, it would be likely voters. And three different definitions that Herrick includes, which I'm not worried too much about. I think the first one is most helpful, but it's good to know that these things are three different things: median, mean, median, and mode. And these are different types of average. Mean is the way we typically use the term average, the arithmetic average of the series, add the numbers together, and then divide them by the number of things that are being added. Median, that's the midpoint, and mode would be the value of the curves. The most often, talk to your stats professor about when median and mode are most helpful. I think mean in most cases is most helpful. All right, last, inference to the best explanation. This is another inductive form of reasoning. And Herrick gives us 8 different criteria to use to judge a candidate explanation for some phenomenon. And you can use this stuff to think about explanations for why things are happening politically. You can use this explanation to think through various economic and state conflicts. You can also use this to think through what some might consider conspiracy theories. Here's that first criteria. Is it internally consistent? Is there any self-contradiction within the explanation itself? Number 2, is it externally consistent? Does it conflict with established and reputable background knowledge? Number 3, is it wide in scope? Does that explanation explain a lot? Does it explain a lot of the evidence? Number 4, has it explanatory power? Does it make sense of what's being explained? Does it really have that logical connection? Number 5, is it testable? And does it test better than competing explanations? Number 6, is it simple? Using what's called Occam's razor here, fewer assumptions, all else equal, mean fewer points of failure, and it's probably going to be a better explanation, all else equal. Doesn't guarantee it's going to be best, but it's helpful. Number 7, is it fruitful? Does it produce new insights? And number 8, does it cohere? Does it logically link up with existing knowledge? Now, we're going to put these to the test or help us understand these by applying them to a particular case. And it's the case of the Mayberry art heist. I'm going to tell you the story. It's on page 276. And then we're going to consider seven different candidate hypotheses as to who the culprit is. And then we're going to evaluate them according to those criteria that we just previewed. All right, suppose a Jackson Pollock painting worth $1 million has been stolen from the Mayberry City Art Museum, and Detective Barney Fife has been assigned to the case. Among the known facts in need of explanation are the following. The burglar broke in through a glass skylight in the museum's ceiling sometime between midnight and 3 a.m., cutting his hand in the process. Ooh, they say his, maybe it's not necessarily a he. The painting was worth approximately $100,000 on the black market. 2 eyewitnesses reported seeing Mr. Smith, loitering around the painting for several hours on the day of the heist. After being taken for questioning, Smith is found to have a cut on his hand. Fingerprints taken from Smith match fingerprints found on the broken skylight. Blood found on the skylight closely matches Smith's blood type. they didn't have DNA tests in Mayberry back in the day. It is discovered that Smith deposited $100,000 in his bank account the day after the heist, although he has no job and was flat broke last week. In addition, shoe prints found at the scene of the crime match Smith's shoes, and fibers found at the scene match fibers from Smith's shirt. Finally, Sheriff Andy Taylor is known to have been out of town the time the crime was committed. All right, now let's take a look at these competing hypotheses. And let's go ahead and skip to hypothesis number 2. Smith stole the painting with the assistance of undetectable ghosts. Well, if these ghosts were undetectable, they're not testable. And this doesn't seem as simple as H1. So 1 is Smith stole the painting. 2 is he did it with undetectable ghosts. And it probably conflicts with your background knowledge unless you believe in ghosts. Hypothesis 3, stole it with the assistance of aliens. Well, that's also not as simple as H1 and also probably conflicts with your background knowledge. Maybe aliens exist, I don't know. But hypothesis 4, Sheriff Taylor stole the painting. All right, well, it's possible he was out of town. However, it doesn't provide any explanatory power. It doesn't explain the blood type, doesn't explain the cut, doesn't explain the eyewitnesses, doesn't explain the shirt fibers, doesn't give us any of that good explanatory power. Doesn't help us to understand the evidence at all. H5, the painting wasn't stolen, but vanished all by itself. Okay, it vanished all by itself. That's untestable, not something we can replicate. And that definitely conflicts with our background knowledge. Things do not vanish all by themselves. H6, Smith stole it, but actually it never existed in the first place. This explanation, this hypothesis, is internally inconsistent. It's self-contradictory because it says Smith stole it, but it actually didn't exist in the first place. And H7, Aunt B, sweet Aunt B, shame on you, Herrick, for even suggesting such a thing. Aunt B stole the painting. Whatever. There's no explanatory power. It doesn't connect with the evidence whatsoever. And it conflicts with our background knowledge about who Aunt B is and what she would never, ever do. H1, Smith stole the painting. It explains a wide scope of evidence. It's likely to prove fruitful. We start to looking into Smith, we're probably going to find other evidence, and it's simpler than the alternatives. Think about these different criteria that we use to judge whenever you're listening to various explanations for various phenomena. You're probably doing that intuitively already, but now you've done it officially as a real official junior philosopher and critical thinker. Okay, that's chapter 10. Coming up next, we've got chapter 11, Explorations in Inductive Reasoning, focused on the logic of science.